Hello. In this video, we're going to prove a major theorem of real analysis called the Bolzano-Weierstrass theorem. This theorem is concerned with subsequences and in particular the convergence of subsequences. This video is also going to cover one way to prove this theorem, and in a following video, I'm going to record another way of proving this theorem. In order to provide the proof for this video, though, we need to introduce a definition. Okay, so let X be a sequence of real numbers. We will say that the mth term, xm, is a peak if xm is greater than or equal to xn for all n that are greater than or equal to m. In other words, a term from a sequence is a peak if it's larger than all of the terms that follow it. So for example, if maybe here, this is maybe x1, maybe here, this is x2, maybe here, x3, maybe here, x4, maybe here, x5, maybe here, x6, maybe here, x7, maybe here, x8. Okay? So for these terms from the sequence, if the pattern sort of keeps on going this way, maybe I'll say like x9 is there, and it could possibly go that way, but maybe it doesn't jump too far this way. Maybe x10 is right here. Okay, so given this, just these terms here, which of these would be peaks? Well, notice that x1 cannot be a peak because x1 is less than x2, right? And in order to be a peak, you have to be greater than or equal to all the terms that follow you. So x1 is excluded immediately. However, it looks like this could be a possible peak, given the information we have. x2. And why would we believe that? Well, from this picture, we see that x2 is greater than or equal to all the terms that follow it, right? It's greater than or equal to x3, it's greater than or equal to x4, it's greater than or equal to all of these other terms. So that would be a possible peak of this sequence. What would be another possible peak? Well, x3 cannot be a peak because x4 is greater than it, okay? But it looks like, so that's my first possible peak. It looks like x4 could also be a peak, right? Because all the terms in this sequence that we see that follow x4 are less than x4. So we'd say that x4 looks like a possible peak here. And again, we don't know the full story because we haven't looked at the entire sequence, but this is just a picture to kind of get the idea across. Are there any other possible peaks? Well, it looks like x6 is a possible peak, right? Because all the terms that follow x6 are less than it. And then maybe x7, maybe also x7. Because all the terms that follow x7 are less than it. Now, maybe also x8, actually. Possible peaks. Now, x9 could not be a peak because x10 is greater than it. Okay? So hopefully this illustrates the idea of peaks of a sequence. Now, one thing to observe is that if there are peaks, right? If there are any peaks and you have like a set of peaks, then if you arrange them according to their indices, right? Like if I look at, so if I look at x2, comma, what would be the next highest index that is a possible peak, x4, and then x6, and then x7, and then x8. And there could be more peaks, or it could stop. Maybe all the other terms kind of bounce this way or something. We don't know. But notice that if we order the peaks, if they exist, right, it's possible that a sequence won't have any peaks. For example, if you are a increasing sequence, then you would have no peaks. On the other hand, if you're a decreasing sequence, then every term is a peak. But notice here, if we do have a set of peaks and we order those terms from the sequence by their indices in increasing order, we get that it's necessarily the case that we have a decreasing list of numbers. And in fact, I was just reminded that this statement of the theorem is wrong. So let me rewrite this theorem. And this theorem here is the Bolzano-Weierstrass theorem. But before I write that down again, just make sure that this is clear to you that if we have peaks, then we can put them in a sequence, a possible sequence, possibly a list. If it's infinite, it would be an infinite decreasing sequence. If it's a finite set of peaks, then it's just a list of decreasing numbers according to the indices. We increase the indices, the numerical values are going down. Now, maybe before I write down the theorem, I should possibly note that suppose these are all the peaks. Suppose you have a finite number of peaks. Then, since X is a sequence, there's an infinite number of terms that are not peaks, right? There's an infinite number of terms that are not peaks, right? Which means that if we look outside of here, for example, x9 is not a peak, right? If we go from 2 to 8, and 8 is the largest index inside of our set of peaks from our sequence, then x9 here, that's not a peak, so it has to break that inequality for at least one index higher than it, for example, x10. So then we can take x9 and then say that that's going to be at most x10. Well, it's a peak, so it can't be equal. And we see that because x9 is not a peak, there is a term in the sequence that's larger than it. If x10 was not a peak, then there had to be some index higher than it. I don't know, xj. So where j is larger than 10, where xj is greater than x10 because x10 was not a peak. We're assuming that these are the only peaks. So what happens if there's a finite number of peaks is that we can look at all the terms outside of the peaks and then form an increasing sequence, increasing subsequence of the original sequence. Now, one of the major theorems that we've proven in this course is the monotone convergence theorem. If a monotone sequence is convergent if and only if it's bounded, right? Well, in both of these instances, it looks like we can create monotone subsequences of X, which means that if X itself is bounded and we make a monotone subsequence, then that subsequence is also bounded, which by the monotone convergence theorem means that it would converge. So that's why I realized that the statement of the Bolzano-Weierstrass theorem that I had originally was not the correct one, because I know that you need the original sequence to be bounded, and I saw that I didn't have bounded up here. So if this is a bounded sequence of reals. Then X has a convergent subsequence so this is the actual statement of the Bolzano-Weierstrass theorem. Okay? And using this idea of peaks, and more specifically the idea of if there's an infinite number of peaks, then we can list them with increasing indices, which by the way is the definition of a subsequence, so that listing the indices in increasing order for the peaks leads to a decreasing sequence if it's infinite. If it's finite, then we can look outside of the peaks, and every term outside is not a peak, so we can then form a increasing sequence, increasing subsequence, or in the prior case it was decreasing subsequence. Okay, so this is the proof of the Bolzano-Weierstrass theorem, and this is the first version of the proof. Okay, so we're going to say let X equal to Xn be a bounded sequence of reals. Okay. And now we're going to consider the peaks, just like I was kind of vaguely talking about over here. In particular, the sequence either has a finite number of peaks or an infinite number of peaks. So suppose that, let's say, so case one, suppose X has an infinite number of peaks first. Okay. So that was like how I originally started off. Like maybe there's an infinite number of peaks. Okay. So in this case, we're going to order the terms from the collection of peaks by increasing the indices. So I think the notation that I'll use is say, so then we may order the peaks of X, maybe say by increasing values of indices. As follows. Say X M1, comma X M2, comma dot 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 X M sub K, comma dot dot dot. And there's an infinite number of these things, right? And here, I should say, just to be clear, where Mi is less than Mj for I less than J. Okay, so the indices are increasing and we ordered these terms like that. Okay, now, so since these terms are peaks, if I pick xm1, then I know that xm1 is greater than or equal to every term from the sequence with larger indices, right? Now, the indices are in increasing order, so I know that that index is larger than that index, which means that's greater than or equal to that. So since these terms are peaks, xmi is less than or equal to xmj whenever mi is, oh no, sorry, this should be greater than or equal to. Whenever mi is less than mj. Just as we did over here. So what that forms is a decreasing sequence. Thus, x prime equal to x m sub k is a decreasing sequence. Okay. Now, as I mentioned before, since x is bounded, x prime is bounded, right? So since x is bounded, x prime is bounded. It's bounded and decreasing, it's monotonic, right? So by the monotone convergence theorem, it converges. By the monotone convergence theorem, x prime converges. Okay, so that takes care of one of the cases for the collection of peaks for x, right? If x is a bounded sequence of reals and it has an infinite number of peaks, then we can construct a decreasing subsequence of the original sequence, which means that by the monotone convergence theorem, they converge. So now we need to consider the case when there's only a finite number of peaks. Possibly none. It could be the case if there are no peaks. For example, the sequence was decreasing, right? Okay. So in this case, we're going to look outside of the peaks, and then as before, we're going to form an increasing subsequence of x. So if there are no peaks, I'm going to say let m sub 1 equal to 1. Otherwise, let m sub 1 be the largest index of the peaks plus 1. So, for example, when this was a finite collection of peaks, what we chose to be our first term in our subsequence was, so the largest index from our peaks was 8. So we chose our first term outside of the peaks as x9. Since x9 is not a peak, at least one term with a larger index is greater than it. So that's how we know that x9 is less than, for example, this case, x10. Okay. So we chose M1 to be that first possible non-peak. Okay. So then I'm just going to say that since x sub M1 is not a peak, there is some integer M2 which is greater than M1 such that x sub M1 is less than x sub M2, right? And again, just to be very clear, and hopefully this makes sense to you, right? If you're not a peak, then there exists, like just negate this, so there exists some value greater than your current index so that this doesn't happen, right? Which means that xn is less than whatever index value that corresponds to. So that's that. Then again, x sub M2 is not a peak. So there is some M3 greater than M2 such that x sub M2 is less than x sub M3. Again, we're just negating what it means to be a peak. Right? We're looking at all the things that aren't peaks. So continuing this process, we build an increasing subsequence. X prime equal to x M sub K. Okay? So that's a prime if you can't see it. Okay? Since X is bounded, X prime is bounded, so I'm running out of room, but I'm just going to try to squeeze it in. Since X is bounded, so is X prime. And then we just state the monotone convergence theorem. By the monotone convergence theorem, X prime converges. Since those are the only two possibilities for the collection of peaks, either it's infinite or finite, and in both cases, we're able to construct a monotone subsequence. Since the original sequence is bounded, the monotone subsequence is also bounded, which implies that in both cases, X is going to have a convergent subsequence, and we're done. Okay. Now this is actually interesting, maybe more so than the second. Well, no, both proofs are going to be interesting. This is just the first one. The second one is also interesting, but I personally like this one because hidden within this proof, we're also saying something else, right? Just forgetting about the sequence being bounded, in both cases, we're able to construct a monotone subsequence. That's interesting, right? That regardless of it being bounded, we first show in both these cases that we can construct a monotone subsequence. It just happens to be the case that if this the original sequence is also bounded, then we're guaranteed convergence of that monotone subsequence. Okay? So I encourage you to watch this video, write the proof along with me. I didn't write it as clear as I wanted to because of space requirements. So maybe write it out a little bit more clear on your own. And then, especially if you're going to grad school, write down this proof without looking at your notes, right? For example, notice that I didn't reference any notes when I wrote this proof. And it's because I have as a mathematician, I have a lot of experience piecing together what's needed once I know the general idea. And the general idea was to look at the peaks and look at constructing monotone subsequences and then applying the monotone convergence theorem, since it's bounded. Okay? Thank you for watching, and in the next video, I will show the second proof.